right? So this is our three-dimensional coordinate system, X, Y, Z axes with an XY plane, a YZ plane, and an XZ plane. And these three coordinate planes divide a 3D space, which is called R3, an R with a superscript, meaning each one of the number lines, X, Y, and Z, are just a real number line or a number line of real numbers. But it's three-dimensional, so we call it R3. Okay. So they divide 3D space into 8 octants. So just we don't really number them except for the first octant. So the first octant is above the XY plane. Where all three variables are constant are positive. So X is greater than 0, Y is greater than 0, oops, and Z is greater than 0. Okay, and so you'll see lots of problems where they talk about the solid, whatever solid you're studying lies in the first octant, but they won't say that there's a solid in the second octant. Well, you could kind of figure out that one kind of has to be to the left of the first octant, sorry, to the right of the first octant. And the third octant would have to be in the back, stuff like that. We just never refer to them because it's just too ambiguous. Okay, so those are the coordinate planes. Let's go ahead and do one more picture. So I'm going to steal a little bit from that last one. And what I want to do on this graph is draw a point in space. So just real quick, let's just do this. I want to try and make this look good, so I'm being a little careful. That's a rectangle in the XZ plane. And I'm going to draw another rectangle in the XY and YZ plane. So I'm trying to, everything here is a sort of a parallelogram. And that's kind of how you do a good job. You just keep drawing parallelograms and things look nice when you finish. Of course, it's easy when you have an iPad or something with a good bit of software on it. And I'm going to change these to dashed lines, I think. So real quickly, I think I'm just going to, oops, change the way these look. See if this looks okay. Oops, I missed one. Okay. So then maybe, oh, except for jeepers. Try one more time. That's better. Okay, so then I think I'll put a point here, and let's give that guy a name. So that one's going to be P, and its coordinates are going to be A, B, C. So obviously P is just the name of the point. Okay, and then of course these are the coordinates. Okay, and of course that means that you're going a distance of A on the x-axis, a distance of B on the y-axis, and a distance of C on the z-axis. Kind of feel like I want to just very quickly make sure we all agree that this object has a name, and they use the name enough where you kind of want to know. It'd be great if you knew what I meant when I used it. So let me make an image of this real quick over here. I'm just going to draw another one of these and get rid of some of the red here. Okay, so this is a parallelepiped. That's the name of this shape, a three-dimensional object, right? Parallelepiped. It doesn't have to be rectangular. It's what's called a it's called a polyhedron. A polyhedron is a three-dimensional object whose faces are polygons. Okay. It has 6 faces. And opposite faces are parallel. Okay, so just so you know what a parallelepiped is. I'm going to go ahead and again, you can probably just keep continuing to use this figure that we've drawn. But I think I'm going to make another copy of it. Oops, didn't mean to do that. I'm going to make one more copy of this. And again, I would just continue to draw on this. We want to put out a three-dimensional Pythagorean theorem real quick. So maybe we should begin by labeling a few distances. So the first one I'm going to do in green down in the XY plane and call that one R. Okay. And then maybe in blue, I'll come up from the origin to this point ABC. And that's going to be the Greek R, which is rho. Right there. Let me try to make that look a little better. Okay, so just for reference, this letter here looks like a P. It is not. It's pronounced rho, and we spell it R-H-O. Okay, this is just essentially a Greek R. So R always stands for radius, right? And rho also stands for radius, but it's an R, but it's sort of a three-dimensional radius, okay? And I know in physics they use R in both contexts. In math, R is always two-dimensional and rho tends to be 3D. Okay. Any questions? You're going to have to just pipe up if you have any questions. Feel free to interrupt me anytime you like. Okay, so this distance is A, and this distance is B, right? So clearly note that A squared plus B squared is which one?
C squared.
With the picture though. There's no, yeah, look at the picture and find the right triangle.
Rho squared? No, R squared.
Okay, so, yeah, A and B are in the XY plane, so they're adding up to a right triangle in the XY plane. So I'll put the right angle there. And so those add up to R squared. You guys see that? That's a real right triangle. And then you want to kind of recognize, oh, there's another right triangle here. So let me go ahead and make this, try and make it clear. So the other right triangle is, is this guy. So like this. Okay, so you see that? And so the height of that side, of course, is C. Okay. So what's the Pythagorean statement there?
C squared plus H squared equals rho squared.
C, yeah, that's an R, but yeah. So it looks like an H. Huh? Let me make that more clear. Maybe that's causing confusion. So this is R down here. Okay. Yeah, so C squared plus R squared is rho squared. So we're going to say it this way. We're going to say also R squared plus C squared is rho squared. And then just kind of recognize A squared plus B squared is R squared. So those can combine and just say thus. A squared plus B squared. What's the rest? Combine the two, what do you get?
Plus C squared equals rho squared.
Right. Okay. So this is our three-dimensional Pythagorean theorem. That allows us to do distances in space. So if we want a 3D, I guess that this whole thing goes under the heading of the 3D Pythagorean theorem. I'll copy that up real quick. Okay, and so that'll give you the diagonal of this parallelepiped that has rectangular faces. The length of the diagonal, which is rho. Okay, and of course that becomes a distance formula. So I think what I would do is copy this one down and just forget about the coordinate system. So let's real quick sketch another parallelepiped like the one we did on the right here. I think I got that. So down below, we're going to do a 3D distance formula. Okay, and to just paste in that parallelepiped. Okay. And maybe we could do this. Let's talk about this point on the left being x1, y1, z1. And then up on the right, let's call that guy x2, y2, z2. Like that. And then we want the distance between them. So we'll draw that. And I guess we could call that rho, but I don't think I will. I'm just going to call it capital D for distance. Okay, so and we can kind of break these distances down. Going down and to the left is the difference between the x coordinates. So I'm just going to say that's the absolute value of x2 minus x1, not thinking about which one's bigger. I'll just subtract the two x coordinates to get that distance. And then the y coordinates, absolute value of y2 minus y1 here. And then the height, of course, the difference of the z coordinates. Like that. And so the 3D Pythagorean theorem tells us that d squared would be the sum of the squares of the other distances. Like that. Okay, so the distance from x1, y1, z1 to x2, y2, z2 is square root of the above. Squaring absolute values makes no sense at all, so we're going to drop the absolute values. Because squaring makes it positive as well. All right, does anybody have any questions yet? We'll do an example in just a second, but let's do the midpoint. And I'm not gonna, this is easy enough to prove, but I don't want to take the time. So the midpoint between these two points And I guess now and then they may ask you a midpoint, but mostly this is not a real important formula. You just average the 2 points. You average the x's and then the y's, then the z's. And so instead of subtracting, you would add these and divide by 2 to just average them. And of course, that's a midpoint. That's the definition of the average of 2 points. It's the midpoint. Okay, any questions? So that's easy enough. So let's find the distance and midpoint between the 2 points, which are going to be 4, 2, 9. And the next point, which is going to be 1, 4, 3. Okay, so easy enough. So our distance, so subtracting the x's, so I guess you could do 1 minus 4 squared plus 4 minus 2 squared plus 3 minus 9 squared. Any questions there? So let's see, 1 minus 4 is negative 3 squared is 9, plus 4 minus 2, that's 2 squared is 4. 3 minus 9 is negative 6 squared is positive 36. And if you add 9 and 4, you get 13 plus 36, that's 49. So that's just 7. Okay. Alberto, is that a P? You're probably referring to something way back.
Yeah, that was a while ago, but I got it.
You got it? Was it a
Yeah.
D?
Yeah, it was a bit farther up, but it's fine. I got it.
Okay. Oh, you're talking about the row, aren't you?
Yeah.
Yeah, sorry. So yeah, that's the P, the R in the Greek alphabet is rho, and it looks just like a P. But see, what's P in the Greek alphabet?
Isn't it phi?
Sorry?
Isn't it phi?
It's just pi. Not phi, but pi. When you pronounce pi in Greek, it's just a P. Okay, so it's a little confusing, but that's it. P is pi and R is rho. Okay, let's do the midpoint. So our midpoint M, we're just taking averages now. So you're going to do 4 plus 1 over 2, and then 2 plus 4 over 2, right? Because I'm averaging the x's, then the y's, and now the z's, 9 plus 3 over 2. So 4 plus 1 is 5, that's 2.5. 2 plus 4 is 6, divided by 2 is 3. 9 plus 3 is 12, divided by 2 is 6. So there it is. So it's, this is just the most basic sort of intro to a coordinate system and the kind of the basic computations you have to do in a coordinate system. Okay, any questions? Okay, so then the basic 3D graphs. First, we would do horizontal or vertical planes. Okay, so we're going to need 3 coordinate systems here. I want to make it a little smaller so I can do 3 of them. Hope you guys had a nice break. You probably took classes. I'm sorry. I'm not gonna have room for a third one. I will shrink it down. Oh, pfft. Okay, so if I wanted to do like something like x equals 2, okay? So I would come out 2 on the x-axis like that. So there's a 2. And then what I need to do is just draw a plane where x is 2. It's a little more complicated than that because you kind of need to make sure it looks like it belongs in this space. So what I usually do is I'm just trying to draw lines that look parallel to the ones I've got here. So I'm just going to sort of grab these and copy paste. So that thing is vertical, just like the z-axis. And then I'm going to grab my y-axis and do a top of this and a bottom. So here, that doesn't look too good. So I'm going to shorten it a little bit. Maybe just to there and there. So like this. And then I'm going to copy that and paste it down. Everything's parallel to something. Sure that I did that right. Doing my best here. So something like that. That's good. And this may be a bad idea, but I'm about to do it anyway. I don't know that I'll be that careful on all of these. So let me go a little further here. So this is the plane x equals 2. Every point on that has an x coordinate of 2. Okay, any questions? Okay. And then let's do a y equals. I think I'll do a y equals 3 just for variety. Okay, so that's all I'm going to do on that one, but I'll go ahead and mark this one off. Stylus is a little glitchy today. So I'd have to go out to 3 on that. So there's a 2 and a 1, 1, 1, 2, and then right here will be 3. Okay, and you can kind of see what a horizontal plane will look like. It's pretty straightforward. Let's go ahead and do one real quick. So that guy is z equals 4. Okay, so that kind of help you with a kind of a one perspective for drawing planes. It's not fun and it's not quick. It can be tedious, but we just do our best. Good pictures make a big difference with being able to master some of the difficult calculus problems that we'll do later. Okay, so any questions about that? Just a couple more things here, and then we'll take our break. So that's the very most basic graph where you just have one of the variables equals to a constant, and of course that's a plane. Then there are cylinders and spheres. So cylinders are pretty easy. And I won't do every possible case like I did with the plane. But for cylinders, you could do something like x squared plus y squared equals 4. So there's no mention of z. It implies that z is unconstrained. Equations are essentially constraints on variables, but if a variable is not constrained, then it gets to be everything. So that means that z varies freely. Okay, but x and y don't. Okay, so it just becomes this thing where I don't need to fill that in. So let me clean that up. Okay, like this. So just need 2 of them. Okay, and then I'm going to hide some lines here. So what that means is I am going to hide the back side of the oval on the bottom and make it a dashed line because it's a hidden line. Like that. And then we'll add vertical sides. Like that. And then somehow I need a coordinate system here. And I kind of feel like stealing one of the others. So I'm going to steal one of these guys from above. I don't know if this slants will be right, but I'll see how it works out here. Yeah, I don't like it. So I may tweak this a little. Like that better. And of course, it's a circle of radius 2. So we can just sort of plop a 2 down there and a 2 down there, and that's the cylinder. Okay, so any questions about that one? So you can have x squared plus y squared equals a number, y squared plus z squared, x squared plus z squared. That's cylinders with 3 different orientations. Okay, and I won't cover all of those. And then of course the very last thing is the sphere, which that's pretty straightforward as well. So let's take a moment and draw our best sphere. Okay, so a sphere is sort of an ellipse and a circle. So I always use an ellipse for the sort of the equator of the sphere. Oops. I'm gonna try and level that out a little here. Looks good. And then just a regular old circle. My ellipse, I'm gonna slice down the middle. So it's hidden, got a hidden line in the back. I think I'll move my circle over here like this. Make sure it looks right. Snap that on there. That good? Yeah. Right there, I think. That's good. Now the origin needs to be in here somewhere. So put an origin in the middle, like that. And if you put this, I think I'm going to do an arc coming down from the top here. So this is going to be the top, and I'm going to have an arc sort of coming down like that. Oh, that is not what I wanted. So I think I might need to make it a sort of a parabolic shape to do this. So I'm going to do this and that and this. So this is supposed to be an arc on the surface of the sphere. Bring that up a bit. I don't like that dot. Just another little tweak or two here. So I'm going to move this just a little bit more. All right, maybe there. Nope. Sit down. It's good. And then what I'll do is I'll pick a point on here. Maybe in a different color, like right here. So that point will just be the point, maybe XYZ. Okay. And we'll do like another sort of a radius coming up from the origin, but this is a 3D radius. So this will just be rho. Like that. And what we know is for every point XYZ on the surface of this sphere, x squared plus y squared plus z squared will be rho squared. So for all x, y, z on the sphere of radius rho, centered at the origin, we would have the x squared plus y squared plus z squared is what? Now that's just Pythagorean theorem there. Sorry?
Sorry, I didn't mean to do that.
It's okay. So what's x squared plus y squared plus z squared using the 3D Pythagorean theorem? Now this is true for any point in space here, if this point right there is the point A, B, C, and rho is the distance to the origin, then we know for a fact that a squared plus b squared plus c squared will be rho square, right? It doesn't matter what the point is. If you know the distance to the origin, then the sum of the squares of the coordinates is equal to the distance to the origin squared. So you can here say, okay, the coordinates are not A, B, C, they are X, Y, Z, and the distance to the origin is rho. So X squared plus Y squared plus Z squared has to be rho square. Okay, any questions? And then one last statement and then we'll go on our break. And I'm gonna draw this one more time, but now I'm gonna take the coordinate system out. So same circle, but I'm kissing the X, Y, and Z axis goodbye. I think I'm gonna get rid of everything actually, except for that, and just say the center. I kind of went too far. I feel like I did too much. I want my coordinate system back. There, that's good enough. Okay, so okay, so my center right here is we're gonna do H, I guess K L, like that. And then the radius will still be rho. So I don't need this, but I do kind of want to get this arc back. So I'm going to copy the arc that kind of helps place that point for me. I think that looks good. Okay, so that's a rho there. All right, anybody want to give me the equation? So this is shifted, it's still the circle. The radius is rho. Shifted to the center HKL. And then you guys ought to be able to tell me the equation. Anybody?
What's the third component?
That's an L. I'm so
L.
sorry.
No, you're good. I just want to double check. It'd
yeah.
be H squared plus K squared plus L squared equals rho squared.
Yes. Now it still needs to be an equation in X, Y, Z. Now think about how you did shifts on circles in pre-calc.
It's x plus h squared, k y plus k squared, l plus z plus l squared.
Is it plus?
It's minus.
Minus.
Right?
Yeah, we always subtract when we shift. So x minus h squared plus y minus k squared plus z minus l squared equals the radius squared. Okay, let's go ahead and do our break till